All right, it's recording. Here we go. Exercise 5E, it's called piecewise functions. In the past, it was called hybrid functions because you can have multiple graphs in it. All it is that piecewise functions simply mean that you sketch, and fill this in, multiple graphs on one set of axes. This is done. How do you sketch multiple graphs on one set of axes? Well, it will look really crazy if you draw multiple graphs on one. So what they do is this is done by sectioning the domain. So your x-axis values, instead of sketching them, they have overlaps. What we do is we section it and we say, well, for this section of the x-axis, I'm going to sketch one graph. For the other section of the x-axis, I'm going to sketch another graph. And then for the remainder of the sections, I'll sketch another graph. Okay, and then you put it all together, it's called piecewise, because you get pieces of the function. So here's an example that I made up. It's not in your textbook. We've learnt linear equations, so I've got a simple one, y equals x. So what does y equals x graph look like? And then you've got the second function, y equals x squared, which you learnt in year 9, year 10, so quadratics. So linear, quadratics. And then just recently you learnt y equals root of x, which is a square root function, right? So what I might do is I might say on the x-axis, for the straight line equation, I will only sketch for the x-axis negative infinity, so anywhere on the left side of the x-axis, all the way up until -1. Pay attention to the inequalities. Okay, this is called standard notation. So in the standard notation, you can see this is less than but not equal to. This is less than but equal to. So that equal to matters when you draw it. Next one for the x squared graph. So for the x squared graph, I'm saying, all right, I want you to sketch a parabola, but not for all the x-axis values. I just want it from -1 to 4. So this, again, be careful of when it equals to and it's less than. And then I want you to sketch your third graph. So a root of x function, but not for all areas. I just want it for when it is greater than 4. So what's the challenge when you're doing this? Whilst you understand what I'm saying, you may kind of have a picture in your head already, it's how do you do it? How do you put it onto the axes? Before we do, let's practice our interval notation. So this is going back to exercise 5A. Let's test your memory. How do I write negative infinity where x is the element or the domain for negative infinity up to 1 in interval notation? Hands up if you want to have a go with this one. What's the interval notation for this? Anyone remember? Oh, no one. I'll pick some people. Oh, Massey.
Bracket negative infinity and square bracket -1.
Beautiful. That means exactly the same thing. Okay, so remember, smallest number is on the left, larger number on the right. If it's equal to, make sure to use square brackets. If it's not equal to, use open brackets. Let's have a go with another one. What about -1 to 4 inclusive? Let's go with Lucky. What do you think the interval notation would be?
Open bracket, -1, and then 4 square bracket.
Beautiful. These two mean exactly the same things. One is called interval notation, the other one's standard notation. What about the last one? It doesn't have two ends.
Open bracket 4 to infinity.
Open bracket. Yeah. Like that. Beautiful. Remember, that's positive infinity because it's greater than 4. So all the right-hand sides are hence infinities on the right. Open bracket for both. Okay, so that's your interval notation. Now, when you're writing your function notation or piecewise function, the ones that how we write it, instead of writing y equals x squared, y equals root of x, it takes too long, right? You can get the domains in standard notation or interval notation. You just need to be able to read both of them. But this is what it will look like. You use a massive curly bracket, okay, because curly brackets is used when you're listing. So I'm going to list the functions. So I'm saying the function f of x can be, instead of writing y, what I do now is I write x squared, root of x. You see that? So this is called a piecewise function. So people, when they look at this, they say, okay, so I've got one massive graph on one axis, not 3 separate graphs. And they've got three different conditions here. I'm going to sketch a linear, but not for all x values. I'm sketching it between negative infinity to negative 1. Now, in your textbook, they will usually do a comma. So they'll say, for the linear function, they could give you standard notation, or they might say, x is an element of negative infinity up to negative 1 inclusive. So you can get set notation. Or they might give you in standard notation and they'll say, for the quadratic x squared, I want from negative 1 to 4. Then they might actually really literally write it like that. They might write negative 1 x greater than or equal to less than or equal to 4. Okay, so you can get a variety. Depends on, that's why you need to know how to read both notations. And the last one, I think I'm just going to write x greater than 4, just make it easier. This is called a piecewise function because there are three pieces to make up this one function. It could be 2 pieces, it could be 4. Most of your textbook questions are going to be 3. Okay, now in your textbook, they don't usually do what I just did. I gave you a linear, quadratic, and a surd. Usually they give you linear just to start off with, so you get a bit more familiar. Yeah, so you need to know how to sketch straight lines. So let's visualize what this looks like. If I were to calculate this by hand, I always start off by looking at the intervals because there are clear intervals here. It starts from negative 1 to infinity. So I'm looking at it, I'm saying, okay, so negative infinity up to negative 1, this section that I highlight in yellow, I'm going to sketch y equals x. Negative 1 to 4, so negative 1 on the x-axis, negative 1 to 4, I'm going to sketch the quadratic part. And then from 4 onwards, because it says from 4 onwards, I will then sketch the surd. So that means there are a couple of endpoints that you need to note it here, which is really, this is where it changes. Negative 1 is where it goes from yellow to blue, and 4 is where it goes from blue to red. So I start off by looking for endpoints. That's what I mean by endpoints, okay? Because that's where the shift changes. So at negative 1, let's have a look at that. At this point, I want to know where's my linear graph going to be at. So here we go. At x equals to negative 1. If that's my function at negative 1, what would f of x be? So f of negative 1, if I sub for the linear graph, what would it equal to? Negative 1, because the rule was x. So if x is negative 1, well then it'll just be sub x in, and that gives you negative 1. For those who are used to seeing y equals x, all I did was I said if x equals negative 1, sub it in. And so it means that at x equals negative 1, the y value is also negative 1. So where's that? Where's that? That is, let's have a look on the accounting. So that's negative 1, negative 2, negative 3, negative 4, and then negative 5 there. Okay, so negative 1 must be right here. Now the question is, do I use a closed circle or an open circle at negative 1 for the linear graph? So look in the notation. Can I have negative 1 for this graph? Yes, because it's inclusive. Okay, so that means I'm going to do a nice full dot for the linear graph. Now, what does a y equals x graph look like? Well, we know a y equals x graph literally is 0, 0, 1, 1, 2, 2, 3, 3. Those are your dots for a linear graph, right? So this is what it should look like. 0, 0, 1, 1. Don't draw this in. I'm just trying to picture it for you. 3, 3, 4, 4, 5, 5. The problem is, if you sketch it, you're sketching the entire x-axis. But which part do you want? You only want this part. So that means this is the only part of the straight line I need, starting from negative infinity up to negative 1. So your part of your linear graph is you only need that section. What I don't need is everything else. So when you sketch it, this is why it's only a piece of it, and you should only be sketching this point to this point to this point. Like that. Does that make sense? Okay, so this is the first graph. From negative 1 to 1, so you got to label the coordinates. That's negative 1, negative 1. That's the end point for the linear graph, which I've just done. For those who can't visualize what I'm saying, I'm going to draw it on Desmos so you can see all three functions. Let's go. I made it on Desmos before. Is it this one? Okay, here we go. This is your three graphs that you have. X squared, root of x. But remember, I'm not sketching on a full graph for every one of them. Each one I'm doing a little condition. So for the first one, we said I need it, so I use a curly brackets if you're using Desmos. Negative inf d. If you don't know how to do the infinity sign, you literally do INF and then t. Y. So you press the Y and it turns into infinity. Okay, so inf d, comma, all the way up to -1. Oh, sorry. X less than or equal to -1. Can you see how that linear graph now is cut off? So if I took off the domain, if I deleted this, if I just delete that, can you see how there's no more straight line? That's the straight line, but I don't want all of it. I only want it from negative infinity all the way up until -1. So that's why the graph stops here. Okay, so that's one piece. What's the next one? I need to do the x squared graph. Let's have a look. So I need to do the x squared graph between -1 to 4. So we have to now work out at -1 and 4, where would the quadratic graph get cut off? Okay, we want to know where it stops and starts. So same thing again, let's do it again. At x equals to -1, so I'm going to do it in a different color now. At x equals -1, for your quadratic, what would y equal to at -1? 1. So that means at this point, y quadratic should start off at -1 squared, and that tells me 1. So I've now got a point up here instead, in green, -1, 1. I know a quadratic graph is meant to look like this, but we're not sketching all of that. We know it starts off at -1, so it goes to 0, and then we said it should curve all the way up until 4, so now I need to know the endpoint for the quadratic. So we do the same thing again. At x equals 4, the quadratic will equal to 4 squared, which is 16. So that means at 1, it should be 16, which is up here. 1, 16. So I expect my quadratic graph to kind of look something like that. It's a bit squished there. Okay, but instead of the entire thing, I'm getting, oh, not 1, so what am I doing? 4. 4, 16. Over here, 4, 16. And there we go. So that is the portion of the quadratic. So if I go back to Desmos, we expect it to look something like that. Rather than this big green graph, I'm restricting it from -1, x equals to 4. Can you see how the graph now gets cut off? But you got to be careful. What did I do wrong in my graph so far? Because if this was done in a sack, you'd lose a mark already. Beautiful. Endpoints, you got to check your domain. The domain matters. I said don't include the -1, but do include the 4. So that means for this one, you lose a mark if you use a closed circle at this end. What it should have been is right here, it should have been labeled as open circle, and then you label it -1, +1. Okay, so it has to be shown as a positive open circle, and here is okay to have a dot. All right, so that's why in my notes on the bottom it says what makes this tricky is you have to be careful of the domain or the endpoints. So be careful when you're sketching these. They'll get tricky. Some of them is open, some of them is closed. You have to check your endpoints. All right, so here we go. We've got my linear, quadratic. Next one's a surd. But the surd, the square root function, I said I only want it from 4 onwards. So really the only other endpoint I have to work out for the square root function is starting off at 4. So let's do it again. I'm going to do it in blue this time. At x equals 4, my function, which is y equals root of x, root of 4 gives you 2. So that means at 4, I expect it to start at 2. So here at 4, remember the square root function is meant to look like something like this, right? But it's now starting off at 4, 2. So that's around here. Is it open circle or closed circle? Open. Very good, because it's not inclusive. So here it's 4, 2. And I expect it to continue going. See what I'm doing there? Those are your 3. That's called piecewise function because you're sketching 3 of them on the one axis, but they are sectioned by its domain. By doing this, it trains a couple of things. 1, you're revisiting your graphs. 2, endpoints, so your algebra. 3, function notation. 4, domain and range. Yeah, so that's why it's a really nice exercise to tie in, and it gets you to practice and watch out for certain details. Yeah? So if I do it on my Desmos again, we've done linear, quadratic, so that's the 416 there. Problem is the square root. We shouldn't have 0, 1, 2, 3. It should start off at 4. So there, this is what I do. I go, comma, open brackets, x must be greater than 4. And that is what you should expect. See that? So that's your linear, quadratic, and your search should have been continuing on. That's the graph, which is what we just drew. Make sense? Cool. So the one that I just gave you, that's a bit trickier because you've got multiple different graphs there. The one in your textbook, they will always stick to linear equations. Okay, so this is an example. You could have negative x minus 3, x minus 5, 3x minus 15. I've set up the table so that you can practice. So finding x-intercept, y-intercept of each straight line. I've already made the chart for you so that it should fit within this realm. And if you follow the endpoints like I've shown you, so clearly it's between 1 is the clear one and 5 is the next one. That helps you to organize it so that you can section it off. That's pretty much 5e. So far so good? Okay, so that's 5e. Take your time, but what it's nice is it trains your reading hybrid functions or piecewise functions. It's just training you to read. There are 3 different functions there and learning how to read the domain. Okay? I'm going to give you, let's say, yeah, we still got a bit of time before we do the next bit. Let's give you 7 minutes. Have a go at sketching this. 7 minutes. I want these 3 with the correct domains. Make sure the endpoints are correct. I want you to sketch this hybrid function in 7 minutes. That brings us to 10:50. I'm going to pause the video. All right. Checking your answers. For the first graph, at x equals 1, you should have -4. So is it inclusive? It's not inclusive at 1. So it should be open circle here. We know that this line has an x-intercept and a y-intercept of 0, -3, and -3, 0. So it should be closed here. And it should have a graph that kind of looks like that. So that should be 0, -3. And it goes that way. So that's your first graph. So your linear graph should be heading that direction. Crosses through 0, -3. That's -4 there. Next one. You have x minus 5 has an x-intercept at 5, 0 and a y-intercept at 0, -5, which means usually this graph should cross through these 2 points, right? But we only sketch it from 1 to 5, or 1 to 5 only. So we got to know what is that 1? And we know that at x equals 1, 1 minus 5 is -4. So it so happens that for the second graph, it does touch at 1, -4. So when x equals 1, for the second graph, it's at -4. And we know the x-intercept at 5 is 5, 0. Hence, at 5, it's 0. So I now have this line. So that's your line for x minus 5. And then for your last line, 3x minus 15, at x equals 1, we didn't need because it's not part of the domain. Remember, the domain says that x has to be greater than 5, so this value is not needed. But the value at 5, it's at 0. So that means when it's 5, it starts off at 0, and your job is to figure out what does this graph look like. Well, logically, if -15 is somewhere down here, you can see that the y-intercept is down here, so it should have been something like this. But you don't sketch all of this, you only start from that point. So it should be like that. And steeper. Sorry, let me just do it again. You expect it to be steeper. Something like that. Hands up if you got a nice joined graph where it's all inclusive here, just because the other ones weren't inclusive, but the second one is, therefore it should all be dots. Hands up if you got that. Very good. Okay, so if I do it on Desmos for you to see, this should be the graph. Here we go. Oh yeah, I forgot. It should have been less than 1. Whoops. Less than 1. There you go. That's what the graph should look like. Less than 1. But if it was a greater than 1, you can still sketch it. It's just that it would have been a bit more confusing, but you would have had it that direction if it was greater than 1. But I wanted you to do it for less than 1. So less than 1, 1 to 5, 5 onwards, 3 linear graphs. That's called piecewise function. Easy? All right. We've got 3 minutes just to take some notes for the last bit. Here we go. Next exercise 5F. This is literally what we've been practicing. On your CAS calculator, you know how I tell you to define your functions? That's all you're doing in exercise 5F, is learning to read the notation. So let's read this one. Instead of using y's now, you are trying to get used to using function notation. Write this in. Here's an example. Instead of y equals to 2x plus 1, we write f of x equals 2x plus 1. Your job is to understand, what does f of 0 mean? Now, I taught that previous lesson. Let's test your memory again. What's f of 0 mean? Yeah, this is just saying whatever x is, I'm replacing that with a 0. So what it's saying is, well, if your function is 2x plus 1, then f of 0 just means 2, and replace that x with a 0 plus 1. So it's really just saying sub x equals 0 into your equation. Find y. F of 0 is your y value. So 2 times 0 is 0, 0 plus 1 is 1. And what does that mean? This just means when x is 0, so this is your x coordinate, you subbed into the equation, the y coordinate is equal to 1. So literally, if I write f of 0 equals 1, you are meant to look at this and say, oh, when x equals 0, y equals 1, that's the coordinate for this function. That's called function notation. And at the start, for a lot of students, this is tricky. Okay, because you're used to seeing y equals 2x plus 1, sub x equals to 0, find y. That's how you've been trained. We're now trying to reduce that amount of sentences, and we're saying one notation. So when I say f of 0 equals 1, that's what I'm saying. I'm saying sub x equals 0, what's the y value? The y value equals 1. That's what it means. Yeah? Let's read the next one. What does it mean if I say f of 1? What does that mean? What's f of 1? X equals 1. So this means in this equation, what if x equals to 1? So in this case, it'd be 2 times 1 plus 1 ends up being 3. But what does that mean? That literally just tells you that when x was 1, you figured out y was 3. So your textbook, they'll train you to read it like this. They'll say f of 1 equals 3. That is synonymous. These two are the same. You're used to seeing it as 1, 3, and that's y equals 2x plus 1. We're trying to change that. That's too many steps. So we're saying function equals 2x plus 1, and if you say f of 1 equals 3, what they're telling you is that when x is 1, y is 3. That's all they're saying. So this is the x coordinate, f of 1 is the y coordinate. Okay? And then in the test, I like to put in the next one. So most students will get this after they practice a bit. And then I throw in a curveball and I just say f of a. And you'll see the number of students that will leave this blank is crazy. They'll get these first two, but they won't get that one. What do you think the answer is for f of a? Yeah, literally. Exactly the same techniques I just did. 0, that's a 1. Well, then it'll just be 2 times a plus 1. And that just gives me 2a plus 1. And all it just means is that when you sub in A as your x coordinate, your y coordinate is equal to 2a plus 1. That's all it means. Okay, so you just got to be able to relate the two. This is what you're doing in 5F, practicing the notation. Now let's see if you can read the second line. What do they want you to do here? When they say solve f of x equals 11, what does that mean?
11 equals 2x plus 1.
Yeah. See, you got, normally in the past it was y equals to 2x plus 1. All we're saying now is the function is equal to 11. So we're saying, let y equal to 11, solve for x. That's how you did it back then in year 9. We say, if y equals 11, find x. But that takes too long to say. So what we do now is we say, solve f of x equals 11. It means the same thing. It means when y equals 11, solve for x. Because I don't know what x is. Does that make sense? Okay, so instead of what you used to do, where we say, this is your equation, find x if y equals 11, that's too long. So what we do instead, we now say, all right, since f of x is equal to 2x plus 1, find f of x equals 11. And that means the same thing. Those two mean the same thing. Okay, it's just written differently. So when you solve for it, f of x is equal to 2x plus 1, and that's meant to equal 11. Do your linear equations. 2x equals 10, x equals 5. Okay? And if you do it on your cows, you can do that as well. This is exercise 5F. Cool? Turn over the next page. I'm going to pause the video. I want you to have a go with this one now. Read the notation from here. So assuming you followed the steps, you would have got b equals half, a equals -3. Let's do the last one. F of x equals 0. Well, since I now know a and b, then my equation now is f of x should be a, which is -3, plus b, which is half x. You're trying to solve for when f of x equals to 0. This is meant to equal to 0. So the y value is meant to equal to 0. Solve for x. Plus 3 on both sides. Times 2 to both sides. Have I gone too fast there? You got it? Add 3 to both sides. I moved it over here. To get rid of that divide 2, I times both sides by 2. So double of half is 1. So 1x, and double of 3 is 6. X equals 6. Okay, so when they say solve for f of x equals 0, really they're saying if y equals 0, solve for the x, which really is just the x-intercept. Okay? All right, team, I'm going to finish the video there. That